concerned about the vulnerability state machine. So what constitutes the vulnerability signature or shield policy is really the specification of this vulnerability state machine, as well as how to recognize and react to the exploits at this vulnerable state, V4. So next I'm going to talk about the shield architecture design. So there are three essential goals to design the shield system. First, we need to allow enough flexibility and minimum effort to support any application-level protocols. So when you have a new vulnerability discovery, you want to be able to author these vulnerability signatures fairly quickly. And secondly, we want to ensure shield fidelity. What that means is we want the shield's interpretation of the protocol context to be consistent with that of the application. Any inconsistency will open opportunities for the attackers to attack the system. Lastly, we also want to minimize and limit the amount of state maintained by shield. We don't want shield to be an alternative target of a denial of service attack. But the bar here is not very high because we only need to design shield to be as DOS resilient as the actual application. So now I'm going to talk about each goal, how we address each goal in turn. So on the flexibility aspect, basically, we use the well-known computer science principle, separate the policy from the mechanism. So the mechanism here is really the generic elements of all application-level protocols. For example, the finite state machine, and the event dispatching logic, and the session maintenance logic. And the policies really refer to the varying aspect of individual application-level protocols. For example, how do we know which application this traffic, this byte stream belongs to, and how do we identify, which event this byte stream corresponds to, as well as vulnerability state machine transitions. And we have designed a shield language to specify such policies. So now I'm going to walk you through the shield architecture. So basically, there are two data structures. On the top, it's the application specification. Basically, that encodes on encodes the policy, the shield policy. And at the bottom here is the session state. For each session, we also have a data structure maintaining the session state. So these are the modules in the shield system. Basically, when there's a new vulnerability discovered, a new policy is authored, and they're being loaded into the system as an application specification. So at the runtime, you receive a packet, and the payload of the packet first goes through the application dispatcher. Based on which executable, which process image this packet is associated with, then we decide, we know which policy to use. So then that's the policy. The policy, again, encodes, what's the state machine transitions and how to recognize the events and all that. So that's basically the guideline on how we interpret the traffic from that point on. Then the session dispatcher, based on the information like from the policy, like how can we obtain the session ID, how can we obtain the message type, and how can we understand the boundaries between the messages. Then we understand what's the event, what event this byte stream represents for which session. So then the state machine engine, based on the current state from the session state data structure, and that event, we consult the policy again. We understand which handler to invoke at that state with that event, and then we interpret the handler. And what handler does is really parses the message payload, and trying to inspect the message and to see whether an exploitation is happening. If it does, then we drop that packet or we tear down the communication session. At the end of the execution of each handler, we always set the next state for that communication session and update the session state data structure. So that was the overall system. This is overall how the system works. Now I'd like to talk about the fidelity aspect, how we ensure that the interpretation of the protocol context in shield is consistent with that the application. The infidelity will result in either the attackers evading the detection, or resulting in false positives, resulting in the disruptions in the services. So there are a number of sources of inconsistencies. So basically, the protocol or message format can be misunderstood by the policy author. Well, we can address that through debugging or test, like trace-driven debugging, or using the existing protocol test suites to address that. And secondly, the event dispatching logic could be inconsistent. For example, it's wrong to use socket as a unit of dispatching. You should not, according to this socket, I should dispatch this event to this session, because there can be multiple sessions going on for that socket, and vice versa. Similarly for the host pair. Host pair should not also be used as a unit of event dispatching. There can be many communication sessions going on between two hosts, obviously. So the key lesson we learned here is that the session is really the abstraction for event dispatching and the unit of shielding. Session is really what the state machine is modeling for. Another thing is that message can be arrived over multiple packets. It's wrong to treat a packet as a message, as this has been done in some of the intrusion detection systems. This has also been pointed out by some of the prior work. So basically, here what we need to do is that we need to do a message-based inspection rather than packet-level inspection. So on the third goal, the minimum state in Shield. So basically, the session state we need to maintain is the current protocol state and the current parsing state and the handler continuation. What handler continuation is that you receive a message, and you can execute the handler as soon as you can. You receive some bytes for that message. However, you may not have received the complete message. Then the handler needs to be halted and wait for more bytes to arrive. So the handler continuation is exactly the same as the call continuation concept. So in terms of the parsing state, you may wonder, oh, gee, parsing state can be huge. There may be a huge message that you have to buffer, like rather long messages. But actually, that's not the case, because for parsing here, we're not parsing to do application logic. We're parsing here to check for the exploitations. So we only need to parse in order to do so. So we can skip a lot of fields that we don't care about. In fact, we only need to keep track of what's the current field that we're parsing. We only need to, for example, if you parse a long message, and you only need to keep track of this, maybe the last 4 bytes representing the data that you're interested in. Maybe you only need to store the partial field that you're parsing right now. So the state there is also not very much. So now I'd like to give you an example on our Shield language. Shield language basically allows us to specify the protocol variations of each protocol and the vulnerability signature that uses that protocol. So here is an example for the vulnerability behind the blaster worm. So at the top is saying that it's a shield, and the first is the name of the security bulletin number for that vulnerability. It's using a TCP, and those are the ports that we're concerned about. Then in the next 2 lines, we specify how we retrieve the session IDs out of the message. For example, it's at offsite 12 for 4 bytes in the message. That represents the session ID of that message. Similarly for the message type. So that's offsite 2 with 1 byte that indicates what the message type. These information are used for session dispatching. And so then here we listed the states that are involved with the RPC protocol. And the next we specify what the events. Basically, if the message type is 0B and in the incoming direction, then that's RPC bind message. So we'll further specify the protocol state machine transitions. Essentially, this is the vulnerability state machine transitions. So at a particular state, if you receive a particular event, you invoke the handler. Another important